This is component 3, lower 6 in class question book, and we're on to question 4. So we've got some oxygen hemoglobin dissociation curves. There'll be a little link in the corner to our fantastic video on these. And we've got the usual S-shaped curve. We've got different lines on there which represent different partial pressures of CO2, so different concentrations of CO2. Our axes are, of course, on the bottom, partial pressure of oxygen, which means concentration of oxygen, and up the side, saturation of hemoglobin with oxygen, which means how much oxygen is attached to hemoglobin. State the name given to the difference in position between the three curves as a result of an increase of partial pressure of carbon dioxide. So this curve shifts which way if we increase CO2. So we've got 2, 4, 8, so it's shoving it to the right. So curve goes to the right. I think you'll know this. This is the nice easy starter to the question. That's our Bohr effect or Bohr shift. B-O-H-R effect or shift. Right, the table shows the partial pressure of oxygen, PO2, and carbon dioxide, PCO2, at different sites in the human body. So these are common sites that they would use for these questions: lungs and muscles. And we've got oxygen and CO2. Okay. The graph shows the O2 and CO2 typically in the lungs. It's 96. So this is really, you look in the table, and if you get 96 as well as a question, then you know you're doing it. You know you're doing it right. So let's just see if that's true. So in the lungs, we have got oxygen of 10. Well, we don't really need my little ruler there, because 10, we're going up there. So that was our lungs. And do we agree with 96? Well, that would be 2 squares down from the top. 96, that looks about right for 96, doesn't it? So we think we're doing this right now. So all we need to do is do the same for the other two. So at rest. So muscles at rest. Because it says muscles there, and now at rest. So we make sure we're reading the right number from the table. At rest we've got oxygen of 4. So we're just going to draw a line up on our graph up from 4. You can do this in the exam as well. It kind of shows the examiner as well the method that you're using. And the CO2 of 4 as well. So we need to choose one of these lines. So it's the 4 one. Which one is that? That's the middle line. So from where that middle line intersects, and that goes across there, 60, 70, 80. So that is 70%. We don't need the units is already there. And we're just going to do the same. So if you can do the first one, you can do the second one. Muscle tissue during exercise. So exercise, and we're looking at 1 for oxygen. So halfway between the 0 and the 2, so that's 5 small squares. So that's going up. Something like that. And the CO2 is 8. So which one are we using for CO2? It's this 8 one here, which is the right hand line. So wherever that right hand line intersects, that's where we're going, and that is conveniently on the 10 line. So we're going to go for 10% there. So just math skills, reading graphs and choosing the numbers that you're going to do that with. Now here's some biology. Explain the significance of the effect of an increase in pCO2 for respiring muscle tissue. This question is just repeated in exams. If you've done the Moodle questions, you'll be able to answer this straight away. So tell us what the Bohr effect does really. And it reduces the affinity of hemoglobin for oxygen. So reduces the affinity, and that's the word used in the booklet, in the notes, everywhere, pass mark schemes, that affinity. And you've got to have an affinity of something for something else. You just can't have an affinity on its own. So of something, hemoglobin, for oxygen. And you could say that in another way, and dissociates at a higher partial pressure, but let's just keep it simple, shall we? And the second mark, well, explain the significance. Well, what happens? Why does this change anything? So more oxygen is unloaded or dissociated from the hemoglobin. So more O2 is unloaded or dissociates, or oxygen is released from hemoglobin. Words to that effect. And those are the 2 marks. And that's just a really common answer if you've done lots of practice questions. Part C, respiratory minute volume. So we haven't met this, but it tells us what it is. It's the volume of gas inhaled or exhaled per minute. And healthy person, 67 dm cubed, that's a litre, litres a minute. And people with diseases such as heart disease, that goes up, so they're breathing more volume of air. So people with diseases like heart disease are breathing more volume of air. That's what it's telling you. Explain how an increase in this volume of air going in and out results in a decrease in the carbon dioxide of blood in the alveolar capillaries. Well, let's just have a recap of what the blood's doing. It's going to the alveoli. Where are those? Those are in the lungs. So we're sending blood to the lungs, and that's been to the body already. So the blood that we're sending to the lungs has got high CO2. And why is it going to the lungs? So that we can get rid of that CO2 that can diffuse into the air and be exhaled. So if we're doing more breathing, we're going to get more CO2 going out into the air. And the question actually asks for, explain how that decreases the carbon dioxide in the blood. So we need to talk about the blood. So our answer of more CO2 is exhaled, or it's exhaled faster. So more CO2 is exhaled, or breathed out. And this maintains this gradient. Why is it exhaled more? Because we've got an increased diffusion gradient. We're replacing the air with ventilating more, and it's keeping that gradient steep. So explain, well, because of an increased gradient of CO2 from blood to air by increased ventilation. Suggest why people with reduced blood carbon dioxide commonly feel tired and lacking energy. So when you read that, you think, well, why would that affect anything really? Well, we're going back to our graph at the start of the question. Remember, if you can't think of what to say for any question later on, go back to the start and it might give you a bit of a clue. Well, we can see from these lines here, if we got more CO2, in the last question that was what our answer was, more CO2, more oxygen dissociates. Well, these guys have got less CO2 in their blood, so less oxygen dissociates, and so they'll feel tired and lack of energy because they've got less oxygen for respiration. So we just need to break that down into our 2 marks. So less CO2, we've got less dissociation. Of oxygen from hemoglobin. Or you could turn that on its head, you could say it's increased affinity of hemoglobin for oxygen. So you could say that either way around, but the end product of it is less oxygen is released or available. Less oxygen is available for respiration, and so they're going to feel tired and lack energy, which is exactly how I feel sometimes, especially when given an equation like this to do on part D. Most carbon dioxide is carried as hydrogen carbonate ions in the plasma, and here's a chemical pathway that's in your notes, in the revision notes, on the slides, in the textbook, and you should know some of these things, especially the enzyme here. So we've got over the arrow, so that indicates something is helping this reaction or propelling this reaction. Y is a substance, and Z is also a substance. So X is the enzyme that you will have learnt, which is just a, have you learnt the name of the enzyme? Carbonic anhydrase, which just makes this reaction happen faster. Y is the name of the substance produced, which is the acid produced, and we just need to either say the name of the acid, carbonic acid, or the equation for it. We'll give the equation because that's keeping with the style of the question, H2CO3. If you're not sure how many 2's and how many 3's and so on, well, it's got to balance. So you can see H2's there, and we can count 1 carbon and then 3 oxygen, so that makes sense. That's the only thing, if we add those into one thing, that's the only possibility. But you knew it from revising anyway. And Z, well, we've got HCO3 minus, which is this hydrogen carbonate ion. The only thing that would make that add up would be to have a H plus. You could say proton, you could say hydrogen ion, but keep it in the same style as what you've been given. State one other form in which carbon dioxide is carried by the blood. You could just say, dissolved CO2 in the plasma. That'd be a nice easy way. Or you could go for one of the longer words, carbaminohemoglobin. So again, these are on this on the nice diagram in your notes. So dissolved CO2 in the plasma. Go for the easy one. But you could say carbaminohemoglobin if you want to sound clever. Here we have a table. Concentrations of hydrogen carbonate ions, the ones we've just been talking about, and chloride ions. So you're probably thinking, right, I can at least say chloride shift now. That's the thing I can remember, but I might not know much more about it. In the blood plasma of an arterial entering and a venule leaving respiring muscle. So let's just think about where we are. So the arterial has got high oxygen blood, and that's entering the muscle, and the venule low oxygen blood leaving, that's going to go back to the heart. So that's where we are, and we've got some numbers for hydrogen carbonate ions and chloride ions. With tables, a good place to start with tables is just to go what's going up and what's going down, and then that's why I'll have to explain it. So in the muscle we get hydrogen carbonate ions, that goes up. So hydrogen carbonate ions has gone up and chloride ions has gone down, and we just need to explain that. Well, hydrogen carbonate ions, well, they've been made somewhere and released, and the chloride ions seem to have disappeared, and that's the chloride shift where we're getting hydrogen carbonate ions coming out of the red blood cell, and to maintain that balance, that electrochemical neutrality, then the chloride ions are going in, and we just need to put that into sensible sentences. So let's just say that chloride shift, and they seem to be giving you a mark for merely remembering that in the right context, which is nice. But then there's a nice mark for saying what happens. So the chloride ions diffuse into red blood cells. So chloride ions diffuse into red blood cells, and that's in exchange for these hydrogen carbonate ions, in exchange for the hydrogen carbonate ions, and put HCO3 minus there. So we've got 2 marks, one for remembering the name and one for just saying what goes in and what goes out, which you've learned from your revision. And indeed, if we just said one goes in, one goes out, well, they're going to give us a mark for that as well. So kind of 1 HCO3 minus out, 1 Cl minus in, and then we've got our marks. We've got our marks now, but we're saying why this happens, and it's to maintain the neutrality, or the balance of charge, or somewhere like that of describing it inside this red blood cell, to maintain electrochemical neutrality inside the red blood cell. So it sounded really hard at the start, but merely remembering the name of the process and kind of what's moving in, what's moving out, and why, just from your notes. If you'd kind of regurgitated and spat out the bit of notes that you've learned, you'd have got those 3 marks there.